Hey, welcome! Today we're going to dive into the architectural principles behind, well, pretty much our entire digital world. We're talking about object-oriented programming, or OOP. It's the fundamental design philosophy that lets developers build the complex, powerful, and stable software we use every single day. So let's pull back the curtain and see how this whole thing actually works.
I mean, just think about your phone for a sec. You could be listening to music, getting directions from a map, and texting a friend all at the same time. How on earth does it manage all that complexity without just crashing and burning? This is the exact problem that software developers were wrestling with for decades.
You see, back in the early days of programming, as software got bigger, it became a total tangled mess. Seriously, imagine a giant ball of yarn where every single strand is connected to every other strand. You'd have data over here, the logic that used it way over there, and changing one tiny thing could cause a cascade of unpredictable problems somewhere else entirely. It was, well, just chaos. And it was incredibly difficult to build or maintain.
And that's where a totally new way of thinking came in: object-oriented programming. Instead of keeping data and logic separate, OOP said, hey, let's bundle them together. This brilliant idea brings order to the chaos by modeling the real world right inside the computer. So instead of thinking about 1,000 separate procedures, we can start thinking about concrete things or objects.
So, a blueprint for everything. The core idea of OOP is that we can create a blueprint for anything we can possibly imagine, whether it's something physical, like a car, or something abstract, like a bank account. And this is where we get our main metaphor for today: the blueprint versus the skyscraper.
Okay, so this brings us to the two most fundamental ideas in all of OOP. On one side, you've got the class. That's the blueprint. The blueprint for a bank account defines what every single bank account should have. And on the other side, you've got the object. That's the actual building. Or in our case, it's your specific bank account, created from that blueprint, with its own unique balance and account number. The class is the idea. The object is the reality. So how do you actually design one of these blueprints? Well, it really just boils down to three simple questions. First up, what is it? That's its name, like bank account. Next, what information does it need to know? That's its state, things like its balance and account num. And finally, what can it do? Those are its behaviors, like the ability to deposit or withdraw money. Name, state, behavior. That's the heart of every single class.
And this leads us to our first huge pillar of OOP, encapsulation. The best way to think about this is like the walls of a house. Inside, you've got all the complicated plumbing and electrical wiring. That's your data. You definitely don't want people just messing with that directly, right? Instead, you give them safe public access points, like light switches and faucets. Those are your public methods. Encapsulation protects the internal data from being messed up by accident, a concept we often call data hiding.
All right, Lego bricks for code. Once we have these well-designed, encapsulated blueprints, we can start doing something really powerful, building much bigger things by just snapping them together, kind of like Legos. This is where OOP starts getting incredibly efficient. This is all thanks to something called inheritance. It lets us take a general blueprint and then create a more specialized version of it. I mean, this saves an absolute ton of work because you don't have to rewrite all the common stuff. You just inherit it and then add whatever new bits you need.
Let's make this real. Let's say we have a very general blueprint, a person class. It might define things that are common to all people, like a name. Pretty simple.
Now, watch this. From that person blueprint, we can create a new, more specialized blueprint. This employee class extends person. That one little word means the employee blueprint automatically gets everything a person has, like the name, and then we can add its own unique stuff, like a salary. We didn't have to copy and paste a single line of code.
And this brings us to the key takeaway here. This simple phrase, an employee is a person. This is a relationship is the logical test for good inheritance. It makes our code model the real world in a way that just makes sense. It's logical and way easier to understand.
Okay, code that listens and juggles. We've designed our skyscraper with these awesome reusable blueprints, but a building that just sits there isn't all that useful, right? Now we need to see how OOP helps bring this skyscraper to life so it can actually handle everything happening inside it.
Modern apps, they're not static. They're dynamic. They use event handling to be interactive,
A button object, for example, just sits there and listens for a click event, and when it hears one, it triggers a response. At the very same time, programs use concurrency, or multithreading, to juggle multiple tasks all at once. But when you have lots of users creating lots of events that trigger lots of tasks, you run into a very, very serious risk.
Let's go back to our bank account. Imagine two different threads, maybe one from an ATM and another from an online payment, trying to withdraw money from the same account at the exact same microsecond. So, what happens to the balance? If both threads read the balance, calculate the new amount, and then write it back, one of those transactions could be completely wiped out.
And this is what happens. Pure chaos. You see a withdrawal and a deposit happening, but the final balance is just wrong. It doesn't reflect what happened. The threads are literally tripping over each other, overwriting each other's work, and the data is just getting trampled and corrupted. This is a classic race condition, and it's an absolute nightmare for developers.
But OOP gives us this incredibly elegant tool to solve this. Just by adding one keyword, synchronized, to the method's blueprint, we tell the object to protect itself. This keyword acts like a lock on a door. It guarantees that only one thread can get inside that method at a time. Any other thread that shows up has to wait in line. One word. That's it, and the data is safe. It's a beautifully simple solution to a really complex problem.
So as we start to wrap this up, it's pretty clear that OOP isn't just a handful of programming tricks. It's a whole mindset. It's how software architects think about and structure really complex systems.
It all comes together in these four main pillars. We've talked about encapsulation, which hides all the messy details, and inheritance, which lets us reuse our work. The third is abstraction, which just means focusing on what's essential. Think about a car's steering wheel. You only need to know how to turn it, not the nitty-gritty details of the axle. And the last one is polymorphism, which is the cool idea that different objects can respond to the same command in their own way. You can tell a dog and a cat object to make sound, and one will bark while the other meows. Together, these four pillars are the foundation for building great software.
And this is why it all matters so much. This object-oriented approach gives developers a massive advantage. They can reuse code like crazy, which means writing less to do more. It makes gigantic systems way easier to maintain and upgrade. And because it models the real world, it lets big teams work together on mind-bogglingly complex software in a way that's logical and manageable.
In the end, object-oriented programming provides the structure, the safety, and the scale needed to build everything from a simple little app to a massive global system. It really is the blueprint for our digital skyscrapers. So the only question left is, what will you build?